Look up at the night sky. It seems full of stars and galaxies, but what if I told you our home, the Milky Way galaxy, lives in a vast, empty region of space? This is not science fiction. Scientists now think we are inside a giant cosmic void. It is a place with much less matter than other parts of the universe. This discovery could change everything we think we know about our cosmos. It might even solve some of the biggest puzzles in astronomy today. This huge empty space has a name. It is called the KBC Void. It is one of the largest structures ever found. For decades, we believed the universe was the same everywhere. The KBC Void challenges this basic idea. It suggests that our location is special. Our cosmic neighborhood is not average at all. In this guide, we will explore this incredible discovery. We will learn what a cosmic void is and how astronomers found the KBC Void. We will see how living inside it affects everything we observe. It could explain a major disagreement about how fast the universe is expanding, a problem known as the Hubble tension. We will also look at the strange motions of galaxies called bulk flows, and how the void might be pushing us through space. Join us on this journey to the edge of cosmic understanding. We will dive into the science of dark energy and the cosmic web. You will see how our unique place in the universe shapes our view of reality. What we learn might force us to rethink our models of the cosmos. It could even change our understanding of our own cosmic history. Let's uncover the secrets of the KBC Void together. Imagine being an explorer on a vast, uncharted ocean. Your mission is to map every island, every reef, every current. For astronomers, the universe is that ocean, and galaxies are the islands. For a long time, we assumed this cosmic ocean was uniform. We thought that if you sailed far enough in any direction, you would always find the same density of islands. This idea, called the cosmological principle, was a cornerstone of our understanding. It made our models simple and elegant. But what if it wasn't? What if our little boat was floating in a particularly empty patch of the ocean? To find out, astronomers needed to create a map. Not just a map of the nearby islands, but a massive three-dimensional chart of tens of thousands of galaxies. To build their cosmic map, astronomers relied on several powerful sky surveys. These projects used dedicated telescopes to scan huge swaths of the sky. One of the most important was the Sloan Digital Sky Survey. Another key contributor was the 2-degree Field Galaxy Redshift Survey. Together, these and other surveys provided an unprecedented amount of data for cosmologists to analyze. Automated telescopes would capture images of the sky, and powerful computers would identify potential galaxies within those images. The real work was in the analysis. Scientists had to sift through the information, correcting for biases and ensuring the data was accurate. With the cleaned data in hand, researchers could finally begin to count the galaxies. This process, known as galaxy counts, is a fundamental tool for probing the structure of the universe. But as the numbers came in, a surprising picture began to emerge. Some regions of the sky seemed to have fewer galaxies than expected. To create a true three-dimensional map, astronomers needed to know how far away each galaxy was. The solution lies in a phenomenon called redshift. The farther away a galaxy is, the more its light is redshifted. This gives astronomers a powerful tool to measure cosmic distances. This is done using an instrument called a spectrograph. Within the spectrum, astronomers look for specific features that correspond to known chemical elements. This method, called a redshift survey, was the key to turning a two-dimensional picture of the sky into a three-dimensional map of the cosmos. As each galaxy was placed on the map, a stunning and intricate structure began to take shape. The universe was not a random scattering of galaxies after all. The crucial study that brought this idea to the forefront was published in 2013 by Ryan Keenan, Amy Barger, and Lennox Cowie. They meticulously analyzed data from multiple galaxy surveys, looking at the distribution of galaxies around our own Milky Way. What they found was a significant deficit. In a vast sphere around us, there were simply fewer galaxies than the cosmological models predicted. The KBC team concluded that we are located inside a void that is roughly spherical and about 2 billion light-years in diameter. The density of matter is estimated to be about 20% lower than the cosmic average. To ensure their result was not a mistake, the team cross-checked their findings with various independent data sets. The deficit of galaxies was real. To help visualize the KBC Void, think of the universe as a giant piece of Swiss cheese. The cheese itself represents the regions where galaxies are clustered. The discovery by Keenan, Barger, and Cowie suggests Our galaxy is not in the cheesy part. Instead, we are floating deep inside one of these enormous holes. The structure of the universe is called the cosmic web. The voids are the huge dark spaces between these glowing strands. They are not completely empty but contain far less matter. Supercomputer simulations long predicted a cosmic web with voids this size. Gravity pulls matter into denser regions, leaving less dense regions to expand and become voids. The surprising part, we are living inside it. The data painted a clear picture. Our cosmic neighborhood is unusually sparse and empty. For centuries, a guiding principle in astronomy has been the Copernican principle. It states that our position in the universe is not special or privileged. The KBC Void challenges this fundamental assumption head-on. If we live inside a giant underdensity, then our location is, by definition, not average. It is atypical. This idea that our location can bias our measurements is a crucial concept. Similarly, if we are measuring the properties of the universe from inside a giant void, our measurements might not reflect the true cosmic average. Being located so close to the center of one as large as the KBC Void is statistically improbable. It is not impossible, but it is rare. The discovery of the KBC Void forced a shift in our cosmic perspective. It introduced a new variable into our cosmological equations: our own location. The KBC Void provided a possible explanation for the Hubble tension. If we are in a large region with less matter, there is less gravity to slow down the expansion locally. This could make the expansion appear faster from our vantage point than it is on average across the entire universe. This idea was a game changer. It suggested that some of the biggest puzzles in cosmology might be solved, not by new physics, but by simply accounting for our address. It was a humbling reminder that we are not detached observers of the cosmos, but participants within it. Imagine the universe as a gigantic, intricate building. It has a specific architecture. This grand design is what scientists call the cosmic web. This web is made of four main components: nodes, filaments, walls, and voids. The brightest and densest parts are the nodes. Think of them as the major cities of the universe, huge clusters of galaxies. Connecting these nodes are the filaments. They act like cosmic highways, channeling matter and galaxies toward the dense nodes. While filaments and clusters make up the bright structure, voids dominate the universe by volume. They are a fundamental part of the cosmic story. So, what exactly is a cosmic void? It is a region of space with a much lower density of matter than the universal average. Voids are not completely empty. However, the amount of matter inside them is tiny compared to the amount found in filaments or clusters. The size of these voids can be truly immense. Some, like the KBC Void we live in, can reach up to 2 billion light-years across. The physics inside a void is dominated by a force that pushes things apart, rather than pulling them together. This force is dark energy. The entire universe is expanding, but not all parts expand at the same rate. Voids actually expand faster than denser regions. Where there is more matter, there is more gravity, and the braking effect is stronger. Inside a void, this cosmic push from dark energy faces very little resistance. This differential expansion causes voids to grow larger and emptier over time. Voids are actively evacuating themselves as the universe ages. Where did these enormous voids come from? The answer lies in the very beginning of the universe. The early universe was almost perfectly uniform, but there were tiny, random fluctuations in density. Over billions of years, gravity acted on those seeds. Slightly denser regions attracted more matter, while regions that started underdense lost matter and expanded into the vast cosmic voids. The unique physics inside voids also affects light. As a photon enters a void, it loses energy. Because the void expands while the photon is crossing, it does not regain all the energy upon exiting. This phenomenon is known as the integrated Sachs-Wolf effect. It means that large voids should leave a faint imprint on the light that passes through them. This is a testable prediction. By cross-correlating maps of galaxies with maps of the CMB, scientists have found that large nearby supervoids line up with large cold regions. Galaxies also have their own individual motions on top of this cosmic expansion. These are called peculiar velocities, caused by the gravitational pull of nearby massive structures. We are moving at a blistering speed of over 600 kilometers per second relative to the cosmic microwave background. This motion is a combination of several gravitational influences. The discovery of the KBC Void adds another crucial piece. We are also being pushed from behind. In the world of cosmology, few numbers are as important as the Hubble constant. This number tells us how fast the universe is expanding right now. However, as our measurements have become more accurate, a serious problem has emerged. The two best methods for measuring the Hubble constant are giving us two different answers. This puzzle is known as the Hubble tension. The discrepancy is about 9%, and it is highly unlikely to be due to chance. The first method uses the cosmic microwave background to predict the global average expansion rate of the entire universe. It gives a value of around 67. The second approach is a direct measurement. It uses a cosmic distance ladder, with standard candles like Cepheid, stars, and supernovae, to gauge the expansion in our local neighborhood. This method directly observes the current expansion rate. It gives a value of about 73. This persistent disagreement has grown into a major crisis for cosmology. It is now at a level of about 5 sigma, the gold standard for a discovery. Researchers have scrutinized every possible source of error. Despite intense investigation, no one has found a smoking gun, a clear mistake that would resolve the tension. This leaves us with two main possibilities. Either there is some unknown systematic error, or the tension is real and is pointing towards new physics. This is where our story comes full circle. What if the Hubble tension is not a problem of new physics or measurement error, but a problem of geography? If our local bubble is not representative of the whole universe, then it is perfectly natural that the two methods would give different results. This is the core idea of the void hypothesis. Living inside such an underdense region would naturally affect our local measurement. With less matter, there is less gravity to slow the expansion. We are in a cosmic fast lane. Models show that a 20% underdensity is just about right to explain the entire discrepancy. This solution is elegant because it does not require us to invent new particles or forces. The idea that we live in a region of faster expansion has been nicknamed the Hubble bubble. It suggests the value of the Hubble constant varies depending on the local density of matter. This leads to a clear prediction. As we measure the Hubble constant using objects at greater distances, the value we get should gradually decrease. Astronomers are actively working on tests to see if this is the case. Upcoming surveys are expected to provide much better data to test this prediction definitively. A higher value for the Hubble constant means a younger universe. The Hubble tension is therefore also an age tension. Using the local measurement, you would calculate an age of approximately 12.8 billion years. Using the global value, you get an age of about 13.8 billion years. If the universe is only 12.8 billion years old, we would have a serious problem. It would mean that some stars are older than the universe itself. The KBC Void hypothesis elegantly resolves this issue. It suggests that the true global expansion rate corresponds to the older age of 13.8 billion years, which is comfortably consistent with the ages of the oldest stars. Our Milky Way galaxy is not stationary. It is on a grand and complex journey through space, driven by the gravitational landscape of our cosmic neighborhood. Our galaxy's trajectory is the net result of all these gravitational tugs and shoves, the combined effect of being pulled by distant superclusters and pushed by the emptiness of the void behind us, offers a complete explanation for our high peculiar velocity. The discovery of our place inside the KBC Void brings us to a critical fork in the road of our cosmic understanding. The first path is that the KBC Void hypothesis is correct. We would not need to invent new physics. The price would be to accept that we live in a statistically rare location. The second path is that the Void hypothesis is wrong. This would force us down the other road, into the realm of new physics, meaning our standard cosmological model is incomplete. The next decade promises to be one of the most exciting in the history of astronomy. New observatories will provide the data we need to complete our cosmic map. Our understanding is a map that is constantly being updated, new continents of knowledge revealed by each generation. The story of the KBC Void is the latest chapter to be written on this unfolding map, a chapter that reminds us that understanding the universe begins with understanding our own place within it. If you enjoyed this journey to the edge of cosmic understanding, please like this video and subscribe for more explorations into the mysteries of our universe. Thanks for watching.